Good morning, Vanindal. Today we are going to discuss about induction motor torque equation. First of all, see how this induction motor starts rotating. So see these three diagrams A, B, and C. So here we are shown the stator and rotor. Stator has some windings, three-phase windings, which are placed 120-degree apart and fed with a three-phase supply which is 120-degree apart, so that a rotating magnetic field is produced. A rotating magnetic field is nothing but a pair of poles, north and south poles, keep on rotating. So say this is the direction of the rotating magnetic field. Let us suppose this is the south pole of the rotating magnetic field, so that the lines of flux are inwards into it, and these are the rotor conductors. Whenever this rotating magnetic flux cuts the stationary conductors, some current is induced in this rotor conductors. So as the current induces in the rotor conductors, it also again produces some flux lines like this. So if you see here, there is a aiding of a flux in this direction, because the flux lines here and the direction of a stator flux and rotor conductor flux are in the same direction, so there is a net aiding of flux, whereas here there is a net opposition of flux. So there exists a flux gradient here which tends to move the rotor conductors in this direction. Okay, so in this way the rotor starts rotating. Means whenever the rotor starts rotating, there should be a torque. Okay, so when there is some torque, then only it is possible to move the rotor conductor like this. Okay, then what is the expression for the torque? So basically torque is proportional to flux and armature current. Flux means the flux generated by rotating magnetic field, and current is the current passing through the rotor conductors. Here the cross indicates the current is into the board. If it is dot means it is out of the board. So this is cross. So the cross indicates the current is passing into the blackboard. Means away from us. If you see like this, okay. Then this is the equation for torque. Torque proportional to flux and current. Stator flux, that is rotating magnetic flux, and rotor current, and cosine angle between these two. Okay. As this is alternating current, we should take the power factor cos phi 2 into consideration. Okay, so this is the rotor power factor angle cos phi 2. Cos phi 2 means R2 by Z2, where R2 is the rotor winding resistance and Z2 is the rotor winding impedance. Impedance means it is a complex sum of resistance and reactance. Okay, so cos phi 2. The flux phi is produced by the stator is proportional to EMF E1. Okay, so induction motor is nothing but a rotating transformer with the secondary is rotated but primary is stationary. Okay, so primary is same in case of a transformer or as a induction motor, but the thing is in transformer it is a straight one, in case of induction motor it is a circular in shape, we can say. Okay, and we have seen single phase transformer only, but this is a three phase, whereas in case of transformer the three windings are placed side by side, but here where three windings are placed in a circular fashion with 120-degree apart, and we are giving 120-degree apart supply to these three windings to produce a rotating magnetic field. Okay, so flux produced is proportional to EMF induced E1. Okay, and we know that the transformation ratio in case of transformer are here in induction motor, K equal to E2 by E1. So K is equal to E2 by phi, where E2 is the EMF induced in the rotor and phi is the flux produced, that is the rotating magnetic field, and this rotating magnetic field is appeared in the air gap between the stator and rotor. Air gap means the gap between the stator and rotor. Okay, so this flux phi is the rotating magnetic flux. So phi E2 is proportional to flux phi. Okay, the rotor current I2 is defined as the ratio of rotor EMF under running condition. Okay, so if it is a transformer, if E1 is the induced EMF in the primary, E2 is the induced EMF in the secondary. There the principle is, when the stationary conductor placed in alternating magnetic field, then EMF E2 is induced in the secondary side due to EMF E1 induced in the primary side. Okay, but whereas in this case the rotating magnetic field is rotating in the air gap which cuts the rotor conductors, so an EMF E2 is induced at the time of starting. Okay, that is said to be E2 naught. Okay, while running, that EMF E2 value is reduced. Okay, in case of transformer we don't have SE2. The slip concept is there only in case of induction motor. So slip means relative speed. Suppose we are two friends traveling, one on the one train and another one on the other train. One is moving at 60 km per hour and another is moving at some 40 km per hour. Then your friend will look at you at a speed of 20 km per hour. Okay, so that speed is called relative speed, and that relative speed is said to be slip. Okay, and so here also the stator magnetic field, that is rotating magnetic field, rotates at a speed of ns, that is synchronous speed, and rotor is also rotating at a speed of nr, that is rotor speed, but the rotor speed at the time of starting is 0. Okay, so ns minus 0 by ns, s means ns minus nr by ns, so ns minus 0 by ns will give a 1. So slip is 1 at the time of starting, so rotor emf is E2 at the time of starting, but during running condition there exists some rotor speed nr. So ns minus nr, my ns is a considerable value, which whose value is varied from 0 to 1. Okay, so our value is SE2. Okay, so I2 equal to rotor EMF by rotor impedance Z. Z is equal to R2 plus JX2. Okay, so SE2 by Z2 I2. Okay, now in this expression we got flux which is proportional to E2, and we got current value which is proportional to SE2 by Z2. Then we'll try to elaborate the expression like this. And I already told to you cos pi 2 is nothing but R2 by Z2, where R2 is the rotor resistance and Z2 is the rotor impedance, that is the complex sum of resistance and reactance. We know the complex numbers magnitude has to be written like this. So Z2 is equal to under root R2 square plus S2 whole square. Okay. Then you can write it as torque proportional to flux into current into cos pi 2. So E2 is proportional to flux, SE2 by R2 plus Sx2 whole square is proportional to current, and R2 by Z2, that is under root R2 square plus Sx2 whole square is the cos pi 2 value. So phi I2 cos pi 2. Okay. So if you combine all these things, you will get like this, and this is the proportionality constant 3 by 2 pi ns. How do we got this proportionality constant? That is not required for examination point of view, but anyway we'll discuss how do we got that. See here derivation for k in the torque equation. We know I2 equal to SE2 by R2 plus X2 whole square. Substituting these values of I2 in the equation, rotor copper losses. Rotor copper losses means, so see here, first of all you have to understand what is the equivalent circuit. In case of a transformer, the primary equivalent circuit is like this. I already told to you, transformer and induction motor are similar to each other in construction per stator side. Whereas in rotor side, the main difference is secondary short circuited. If